Hello friends, welcome to my channel. This is Thermodynamics and Power Plant paper, Isro question paper from 2006 to 2016. Part 4. Question is, characteristic gas constant of a gas is equal to A Cp by Cv, B Cv by Cp, C Cp minus Cv, D Cp plus Cv. We know Cp by Cv is ratio of specific heats, it's gamma, and Cp minus Cv equal to R. R is characteristic constant. And here one more thing is important. R is universal gas constant by molecular rate, or sometimes they are writing it as capital M, Ru by M. So from option Cp minus Cv equal to R, C is our answer. Here this is reversible adiabatic process may be expressed as T1 by T2 equal to, we know for adiabatic process, reversible adiabatic process, Pv to the power gamma is constant. From here, P1 V1 to the power gamma equal to P2 V2 to the power gamma. Then P1 by P2 equal to V2 by V1 whole to the power gamma, or V1 by V2 equal to P1 by P2 whole to the power minus 1 by gamma. Let it be as equation 1 and equation 2. Then we know P1 V1 by T1 equal to P2 V2 by T2. From here, T1 by T2 equal to P1 by P2 into V1 by V2. We already got P1 and V1 pressure and volume relation, so put that one. P1 by P2 is V2 by V1 whole to the power gamma, and V1 by V2 we can write 1 by V2 by V1. So finally we will get V2 by V1 whole to the power gamma minus 1. This is T1 by T2 equal to V2 by V1 whole to the power gamma minus 1. Let it be equation 3. Next, T2 by T1 equal to, this one already discussed in my previous video. Whole to power gamma minus 1 by gamma. So here T1 by T2 equal to P1 by P2 whole to the power gamma minus 1 by gamma. This one we got using equation 1, 2, 3. 1, 2, 3. From equation 1 to 3 we got this one. So our answer is T1 by T2 equal to P1 by P2 whole to the power gamma minus 1 by gamma. From option C is our answer. Question is, a gas is so expanded in a cylinder that its temperature remains constant. The resulting variation of pressure versus volume is its temperature remaining constant. So PV to the power n equal to 1 is constant. P1 V1 equal to P2 V2. N equal to 1. This is also important. For isothermal process, n equal to 1. Then equation of parabola is y square equal to 4ax, and equation of hyperbola is x square by a square minus y square by b square equal to 1. Straight line equation is y equal to mx plus c, slope intercept. So from here, equation of parabola not possible, this one also not possible, only equation of hyperbola. B is our answer. According to first law of thermodynamics, A, mass and energy are mutually convertible. B, heat and work are mutually convertible. C, heat flows from hot substance to cold substance. D, Carnot engine is most efficient. This one for second law. Carnot engine efficiency also second law. So B is our answer. Heat and work are mutually convertible. First law. B is our answer. Next, 90 kilograms of ice at 0 degrees Celsius are completely melted. Find the entropy change in kilojoule per Kelvin if T2 is 0 degrees Celsius. Latent heat of fusion is 318.5 kilojoule per kg Kelvin. At constant temperature, only phase is changing. Latent heat of fusion also given. We have to find the entropy. So data given are mass equal to 90 kg. T1 and T2 both are same. It's 0 degrees Celsius. Latent heat of fusion is heat transfer only, latent heat of fusion. So it's 318.5 kilojoule per kg Kelvin. We know entropy change L cube by T. So 318.5 divided by T is, it's in degree Celsius, so it's 273 Kelvin. So by 273 you make it as 318.5 divided by, into mass we have to multiply, because answer in kilojoule per Kelvin, this one asked. So mass also we have to multiply 90 kg mass here, 90 divided by, let it be, here I am doing del is equal to 318.5 into 90 kg divided by 370. 273, we can take it as 270. So for easy calculation, it's coming as 3. Then 0, 6 kilojoule per Kelvin. From option A not possible, B also not possible, D also not possible. Only C and not 5 kilojoule per Kelvin. C is our answer. A perfect gas at 27 degrees Celsius is heated at constant pressure till its volume is doubled. The final temperature is how much? We have to calculate the final temperature. It's a perfect gas. We will use combined gas equation here. Data given, first we will write T1 equal to initial temperature. T1 equal 27 degrees Celsius. In Kelvin it's 27 plus 273, 300 Kelvin, till its volume is double. So first let it be V1, final volume V2 is 2 times of initial volume is doubled. Then constant pressure, so initial pressure P1 and final pressure P2 both are same. We will use combined gas equation. P1 V1 by T1 equal to P2 V2 by T2. Pressure constant, so cancel. Then we have to find T2. So V2 by V1 whole into T1. V2 is 2 V1 by V1 T1. V1 cancel. 2 into T1 is 300 Kelvin. So it's 600 Kelvin. You have to careful about the unit. 600 Kelvin. Here it's in 600 degrees Celsius. So you should careful. Then in 600 minus 273. So you will get 327 in degrees Celsius. This is in Kelvin. So 327 degrees Celsius. C is our answer. Careful about the unit. The stagnation temperature of an isentropic flow of air K equal to 1.4. Here K is ratio of specific heats. In 360 Kelvin, if the temperature is 200 Kelvin at a section, the Mach number of the flow will be how much? We have to calculate that. Mach number M. We know TO by T equal to 1 plus gamma minus 1 by 2 M square. This is very important for IAS exams. GATE they won't ask you this one, but IAS they will ask. For IAS conventional paper also this is important. And one more thing, this one also important. TO by T star, PO by P star whole to the power gamma minus 1 by gamma. These two things are important. Here gamma is equal to K, it's Cp by Cv, it's 1.4, and TO equal to 360 Kelvin, stagnation temperature TO. Then T at a section temperature, it's 200 Kelvin. We have to find the Mach number of the flow. And Here TO is static or stagnation temperature, T is temperature at the section. Here K equal to gamma, ratio of specific heats, it's 1.4, and M is our Mach number, V by C. Here in this formula, put the value. Stagnation temperature is 360 by temperature 200 Kelvin. 1 plus gamma is gamma or K. K is 1.4 minus 1 by 2 into M square. So here 9, 5. It's 9 by 5. So 9 by 5 minus 1 equal to 0.4 by 2 M square. So 0.4 we can write 4 by 10. 4 by 10 2 by 5 equal to 1 by 5 M square. This one also we can write 0.2 M square. So here 9 by 5 minus 1 is 4 by 5 equal to 0.2 M square. So M square equal to 4 by 5 into 5. 5 cancel, it's 4. So M equal to root over of 4 is 2. Mach number is 2. It's greater than sonic velocity. So from option D is our answer. Greater than sonic velocity. Sonic velocity when M equal to 1. Here in this second equation, T star and P star, they are critical temperature and critical pressure. This is also important. Question is, when a supersonic flow is admitted into a convergent, the flow will be supersonic flow in a convergent passage. So its convergent is like this, and divergent is like this, from 1 to flow direction, 1 to 2. Supersonic flow, supersonic convergent, so supersonic nozzle is equal to subsonic diffuser. In supersonic nozzle, here Mach is greater than 1. This is nozzle. This is for diffuser. It will supersonic nozzle act as subsonic diffuser. So M is less than 1. Here at exit of supersonic nozzle, pressure will increase and velocity will decrease. In subsonic diffuser also same thing will happen. Pressure will increase and velocity will decrease. So decelerate flow, B is our answer. That mathematical equation already I told in my previous video. So you just remember these two figures. Both pressure and velocity of steam drops in the moving blades of, this is steam turbine question. Impulse turbine in nozzle pressure energy is converted to kinetic energy. Velocity will increase. And in this question, pressure drop and velocity drop they are asking in moving blades or turbine blades. Impulse turbine, no pressure drop. Pressure drop only in nozzle or fixed blades. In moving blades, no pressure drop. But in reaction turbine, both pressure and velocity drops. So answer is reaction turbine. Both pressure and velocity of steam drops. Reaction turbine is answer. If they will ask for only no pressure drop in moving blade, then the answer will be impulse turbine. The sound of explosion on a ship located 10 km away from the beach was heard 28.6 seconds after the explosion was seen. Estimate the temperature of air at that time. Here little bit calculation required. Without calculator, little bit difficult. Velocity of sound or C equal to sonic velocity. We know this one already discussed. Gamma RT. Gamma is 1.4 for air. R is equal to 287 joule per kg Kelvin. T we have to calculate. And one more thing, velocity V, or in this question it's C equal to displacement by time. Displacement is given, it's 10 km. So 10 into 10 to the power 3 meter divided by time. Time is 28.6 seconds. Then C value we have to calculate from this formula. Put the values 1.4 to 287 into T. C we already got here. So it will come 10 into 10 to the power 3. 28.6 we can write it as 286 by 10 equal to 1.4 into 287 into T root over. So squaring this one, it's 10 to the power 5 by 286 equal to 287 into 1.4 1.4 into 287 into T. So if we calculate this one, approximation method we will use. We will calculate this one, we will get 304 Kelvin. So in option 304 Kelvin is not available. So in degree Celsius you convert it. 304 minus 273. It's coming 31 degrees Celsius. From option A is our answer. So unit also you have to check. Thank you friends. Thank you for watching my video. Thank you.